Can you host an Amish party for us? That'd be.
It's for her birthday. We are going to have it for her. It's happening.
Yeah, when is it?
11th.
Aquarium baby.
Aquarium baby right here, that's right. I will bring the, what's it called,
Did
the
you hear me listening to the same video?
butter churn.
Right?
Wait, can we, it can be like, an activity-based birthday party, like, can we all decorate our own bonnets? Bonnet
2 hours, so that was it.
Okay, Kelly has a great point.
okay.
We're gonna actually have really activity-based birthday party for you, where we're all gonna personally design our own bonnets.
Parties with activities that
Churning butter.
Churning
butter.
Oh my God.
That would be amazing. Who can make the biggest
We should
candle?
let you.
Do it up.
You know me so much. She has horse and buggy. Do you think we could find one? We'll tie like a little like carriage around.
Oh my God.
Maybe a horse trap.
We should make it like an Amish, Amish Olympics.
There's a
That sounds good.
That's incredible. Amish Olympics.
Yes, of course you are. Come on.
Hey, I'm not opposed.
Yeah, and I watched it literally 5 because I like shooting tree and I was laughing so hard.
We just like.
Pressure to cut
No zippers.
You are the weakest link. You're kicked out.
Your son, doesn't think
Yeah, it's Sean.
right?
Sean, you are shunned. Ooh,
We
that's
could have,
neat.
so as like game we play, the loser has to be shunned for the next game.
Can we get a Dunes hat for this too? Is that part of this? I don't know. I have no idea. I don't know anymore. Okay, a ruler.
Oh my gosh.
Do we have to?
Someone has to kneel on the tie.
There you go.
Ooh,
Ow.
Everyone see that?
Yeah, that was scary.
Oh yeah, that's harsh.
It's at the lamp is a
Really,
really
really
end of its beautiful life.
You gotta no that and Kelly.
Yes.
Kneeling on the floor on
Birthday's coming up.
Oh, okay.
Okay, so
Delaney,
we've got a few minutes here. So the exam will be in 246. So it's at 8 o'clock. How many questions are there? Be about 25 to 30. And remember the nature of the questions. I mean, you're working on the question. Go by what the question says. Choose the best answer, but you know how the grading can work on that stuff too. Sometimes partial points are given. So do the best one that you can do that you think is the best. Okay. So clear as mud, right? What this is, you see, with our regression stuff, I'm not going to talk about regression stuff, but regression, residual. These will be computed in different ways in regression and residual, but that's the same source of variation. Okay. Just before we get into this, I also want to talk a little bit. I told you about talking about frequency data. Okay, because in this class, it just doesn't fit in that we talk about chi-square analysis. And oftentimes, like, you run back to your labs and your supervisor, can you do a chi-square? Oh, we didn't cover it in class. Just because chi-square analysis and frequency data is an entirely different topic. But is everyone pretty good on chi-square? You've looked at that in undergraduate. Have you ever looked at chi-square? Okay. The nature of the data in chi-square is different than with this data here because it's frequency data. Okay. And we'll talk about it in Stat 2. But just in case you're not taking Stat 2, if you have a 2x2 table, and these are frequencies 5, 10, 15, and 20, these are the number of counts in the table, right? The number of people that shows A and shows C. Okay, that count data is frequency data, and that's different than the types of data we've been dealing with, because we've been dealing with primarily continuous data. We've had a categorical variable as our independent variable, but when you run into situations like this where you actually have counts instead of like means in the cells, you can see what is this, like a 2x2? It's like a 2x2 analysis of variance, only that there's counts in here, not means. Okay? So that requires a different analytical approach, which one option is to do a chi-square So what would just very quickly, take 2 minutes to do this, what would the chi-square be evaluating here? It'd be saying, do these observed frequencies match up with what you would expect based on chance? And that null hypothesis would be the expectation per cell. Okay, so if we make this 5, 5, and 5, my expectation per cell would be 5, right? So in that case, that null would not be rejected, it'd be meeting up perfectly with expectation. If this is 6 and this is 4, my expectation per cell would still be equal to 5, but what would happen here is it would be a little bit, you experience a little bit of deviation, okay? If you take just a simpler example like this, 5, 5, and 5, if I modify this to 4 and this to 6, well, my expectation per cell is equal to 5, but I have a bit of a deviation. So a chi-square test will analyze that to see if those frequencies are different enough from expectation. Okay. The one that I just put up there, the expectations, actually, I'd have to double check it, that they may not actually equal to 5 per cell because of the way it's constructed, but you get the idea. Okay. Different types of data, and whole courses are taught on frequency data. So you need to do a chi-square analysis, just recognize you're in a different area, and we'll talk about that more into step 2 if you're taking that course. Okay, back to more important matters. So this makes sense. Between, within, consider the generic ANOVA summary table. Can you explain the meaning of the terms and the logic in evaluating? So a general understanding of the logic of how this table works, right? Everyone makes sense to everybody? How this table is working, what these different totals are representing, right? You've got sums of squares, you've got between, sums of squares between versus sums of squares within, those are measuring different quantities. Expectations, right? So the colleague says the expectation, I have an F ratio of 2.3. Is that statistically significant? Well, it's different from 1, but that all depends, right? You still need to do the significance test to see if it's statistically significant and not just different from 1. Right? So if you get an F ratio of 1.2, you have to evaluate that for statistical significance. You can't just say, well, it's different than approximately 1. Make sense? Eta squared from this table, where is it? Where's eta? Grandma eta? We used to call it grandma eta. Where's grandma eta in here? Sums of squares? Between, over? Total. Makes sense, right? Notice that the eta squared is coming from the descriptive part here, right? It's not over the degrees of freedom yet. So you've got your effect size is coming from here, but when you do your F test, you're doing it with the mean squares, okay? So your cheat sheet, how are you gonna construct your cheat sheet? You wanna have that on there, right? You wanna have that on there because if you're asked a question, well, what's going on in ANOVA, you can actually go to your cheat sheet. You don't have to memorize that you're taking mean squares between to mean squares within. You can just say, oh, I remember, yeah, there it is in my cheat sheet, and so I could work out on the problem. Looks good? Difference between eta squared and F. Just talked about that, right? So that's a big central theme, right? Difference between, do you know the difference between effect size and an inferential statistic? Right? That's what we've been talking about in one form or another over and over, because it's so important, right? It's so important that if you see P is less than 0.05, you don't just want to be like celebrating in some way and going, well, we rejected the null. You have to know the difference between statistical significance and effect size, and that's what that's getting at. Eta squared versus F, what's the difference? So your colleague rejects the null hypothesis for the ANOVA and says, I obviously found a scientific effect. Not true, right? Because we know, can you reject the null hypothesis without there being anything really practically relevant? Yes, right? Big important idea there. And feel it and hear a little bit, right? Go, yeah, I get it. I see why that's the case. I see why that's the case. Is that you can reject a null hypothesis, but it just not be a meaningful effect. Likewise, as we saw on the board just a second ago, you can actually have a steep slope. Steep slope would be what in ANOVA? big mean differences. But if those mean differences are based on a sample size of 5, what do you not have enough of? Power, right? You see where power fits into it. Therefore, maybe I don't reject on F. Maybe I don't reject on F, even though my mean separation is actually quite big, right? So the colleague says I have means of 10, 50, and 90. Seemingly big differences. Maybe my effect size is where? In here? Effect size is? Right, eta squared. So maybe my effect size accounts for 70% of the variance. Is it conceivable that even with 70% of the variance, I don't reject the null hypothesis? Yes, right? And I'm telling you, knowing that, you can evaluate a whole bunch of evidence. Just knowing those two are not the same thing. They're not the same. There's a difference between effect size and p-values. Okay, they'll come in different forms and different tests and different whole bunch of stuff, but there's a fundamental difference between the two. So you have a big effect, but you if it's based on a low sample size, you're not rejecting the null. And that's where we said here, made the argument for the p-value. P-value is still important, right? It's still important because it tells you if you have inferential support. Yeah.
Should a p-value always be, because I guess I've read studies where they report an effect size, but then they don't report a p-value.
Yeah.
Should they always be reported?
Well, that's a good question for the class, right? What if so the colleague reports an effect size, you go to the APA convention and someone says, I report an effect size. My effect size is 70% variance explained. But they don't report a p-value because, p-values are lame-o. Who wants to report p-values? Problem with that, right? What's the problem? You don't have inferential support. So yeah, you need the p-value, or at least the ingredients that make up the p-value, right? So if I'm at the conference, I'm saying my effect size is 70% variance explained, and I say, oh, and I got like, 500 subjects that did it. You're like, yeah, you're probably fine. You want to see the p-value? Nah, I've got it kind enough to go because I know what's constructed in the p-value, and you have a big effect size. You've got a good sample size. I have a pretty good guess what's going to happen to that p-value. Makes sense, right? You see the construction of it, right? So, you'd be the one looking at that saying, I don't need to see the p-value, I've got enough information. So, maybe the colleague says, at the conference is saying, what should the colleague ask for next? Colleague, attendee. What's the p-value? What's the sample size? Maybe both of the options are doable, right? Because say, well, if the sample size is pretty good, that p-value is going to be blown out of the water. With an effect size of 0.70, boy, it's not going to take long for that p-value to get less than whatever value you want, right? Makes sense? You'll get less than your 0.05 and 0.01 pretty soon. So then you're all into the effect, right? So sample size of 1,000. What are you most interested in the average study? P-values or effect sizes? Effect sizes. Does it make sense? Right. It's got to be the effect size because the p-value is going to be rejected. Under what circumstance would that possibly not be true? Under what circumstance would you actually, with 1,000 observations, would you actually say, I want to see the p-value? Add up on the board here.
Extremely small.
Extremely small variation in your sample or population where it's like, even with 1,000 observations, that would be really hard to get. There's such small differences in the material that you're dealing with that, no, sorry, I'm gonna need inferential support, right? That's kind of like very, very unlikely, but theoretically it's possible because if the variation's so low, then technically, maybe you still need that significance test to make an inference. So, effect size versus p-value, major theme. How is sample size differentially influential in each? Well, look at your between and look at your total. How do I know what my sample size is just based on looking at SS between and SS total? Now, if I know from the computations, if the computations are there, I know how much sample size went into it. But the thing is that effect size is not influenced by sample size the same way as the p-value. Does that make sense? The effect size is not influenced the same way, right? So I start off at 0 participants. My effect size could do this, could do this, could do this, could do this. Now theoretically, I'd have to check the literature that it actually, the expectation of it actually might rise a little bit or lower. But the point from a practical standpoint is that it's not gonna do this just because you have more of a sample size. Make sense? P-value will, assuming the effect stays about the same. It's guaranteed to happen. You're guaranteed to reject null hypotheses for increasing sample sizes unless what? A, B, C, D, E. Guaranteed to reject the null hypothesis for increasing sample sizes unless under one certain condition, the means are equal, right? The means are, there's no effect. Regression, slope is equal to 0 in your sample. Nothing's gonna happen. You say, I keep collecting sample size and I still don't reject the null because you got nothing going on. There's nothing going on. But as soon as you have something going on, then what becomes the almighty? As soon as you have something going on, then what becomes the master of all? Yeah, but well, in terms of the p-value, right? So something's going on in your numerator. So I hate looking at this, but you have to look at the denominator. Yeah, standard error becomes master of all because that's what's going to determine whether that difference you've observed is actually enough to reject that null hypothesis. Make sense? So you look at whether you look at the t, whether you look at the z, now whether you look at the b coefficient, just to liken that stuff, right? Numerator, it's the denominator that tells you how much variation do you expect to see under the null hypothesis. Makes sense? Okay. Conceptually, what does MS within estimate? What's MS within really getting at?
Error.
Right, just getting at error variability, right? It's getting at the stuff, is that why you did the study?
No.
No, you didn't do it for MS within. You didn't say, I'm really interested in studying MS within. For this type of thing here, you're actually, what do you hope MS within ends up being? Big or small? Small, right? Smaller MS within gives you more power, right? Gives you more power. It gives you more power because that's the bottom of your F ratio. That's the bottom of your F ratio, right? So all of a sudden the numerator is like, you're standing to somebody, am I tall or short? Depends who you're standing next to. So what does it construct? In constructing, why does it make sense to have MS within the denominator? Makes sense, serves as the base, right? Serves as the base. You can see also why the expectation is equal to about 1, because if the F is equal to about 1, then MS between and MS within, they're getting at the same thing. Right? There's no evidence that the between is getting at something different than the within. So 3 conceptually, so we've done that. 4, why does it make sense that the expectation, no problem. We see why it should be about equal to 1. And we say approximately equal to 1, and it's just for theoretical reasons why it's not exactly to 1, but for all practical purposes, that F ratio is equal to 1 under the null, okay? So you're thinking F is equal to 1 under the null hypothesis. If F is equal to 1.2, do you reject? F is equal to 1.2, who rejects the null? It's different than 1. Colleague says, I got an F of 1.2, therefore, A, B, C, D, E. I reject, not reject, do something else.
Compare it to the references.
Right, you get a significance test on it, because 1.2 is different from 0, but you want to determine what's the probability of getting 1.2 under the null hypothesis of equal. Right, sure, that's good. Under the null hypothesis that F is equal to 1, which represents the means are equal, right? Which represents the means are equal. So bring it back to the science, you did it because you want to compare groups. You want to compare groups, so under the null hypothesis, all of those means are equal to one another. What if what if ANOVA did not partition into SS between and SS within? What would be the problem with that? So I told you I did ANOVA, but my partition doesn't work. It just doesn't work, which would kind of be a travesty, but it didn't work. But my eta squared is equal to 0.60. What would be the problem with that? SS between and SS within don't add up to 1. Don't add up to the total, rather. I was thinking effect size. Then what happens to that effect size? It's like if this is different for each data set, then taking SS between to SS total, it's not going to make much sense, right? So when you think of this, you're thinking of you've got the total, then you've got the between and the within, that's the partition, that's the pie, right? So the important thing is that we have the whole partition. We have this, and we're breaking it into SS between and SS within. If this total, SS total, does not partition perfectly into these two things, then my basis for saying SS between to SS total completely falls apart. So my basis for taking eta squared would be completely ruined. So we know for every data set that could ever exist, that partition is gonna be true, and that allows us to do our effect size, our eta squared, and do our ANOVA. Make sense? Okay. Number 6, if the ANOVA were true, what would the expectation of MS between equal to? Equal to about the same thing as the error, right? MS within. That's that MS within over MS between over MS within is equal to 1. Make sense? Justify the maximum value, well, there's a repeat question, right? So eta squared, justify that has to equal 1. How do you justify? Why can't it be greater than 1? Why can't eta squared be greater than 1?
It's a ratio of a part to a whole.
Right, so part to a whole, right? Can you explain it in terms of, see, if you work on the explanation, then you identify which option is right. So why can't it be greater than 1? Well, the total is SS total here, so SS between is what? A smaller, it has to be smaller or equal to SS total, right? It cannot be greater than it, because SS total is the sandbox, it's all the variation you have. SS between is a subset of it. SS within is a subset of it. We know that these two things sum up to this. Make sense? Therefore, you can't have eta squared greater than 1, because by definition, eta squared has to be between 0 and 1 for that reason. Make sense? Okay. Can it be negative?
No.
Why?
Ratio.
Well, yeah, but it's squared, you know, just look at that. I'm not seeing anything squared in here. It's squared for a different reason. I'm not seeing anything squared in here. Why can't this be less than 1? What's this? Well, what's squared? Maybe you're on the right track. Maybe I was like too fast on that one. What's squared? We're referring to SS between is squared? SS between cannot be negative, right?
Right.
Right, SS between, right. These are sums of squares, and these are sums of squares. So where am I gonna get a negative number, right? SS between cannot be negative because it's a sum of squared values. So I'm taking one quantity here that's positive, divided by another quantity here that's positive. These sums of squares cannot be negative. So right away we know it cannot be less than 0. So feel free to like fiddle around with it. If you see a question like that, go like don't be afraid to figure it out as you're working through it. Say, well, why can't it be negative? Let's see. This has to be positive, this has to be positive. Oh, I see. So it's impossible for it to be negative. Make sense? Okay, I'm gonna stop saying that. I'm self-aware and I just noticed I'm always saying it. So I'm gonna say something different. I'm gonna say, is it clear? So, 8. An eta squared value of 0.999 is large regardless of the research context in which it is computed. Do we agree? How could we here's a way to do it too. When you look at a question, think of, well, what would be the opposite of this? Could we disagree with this in some way? And then if you go through things and you say, I just can't disagree with it, then you kind of take the default and say, well, it must be right. So it's large regardless of the research context. What's the question getting at here?
It says close to a maximum.
Well, close to a maximum, right? And it depends on the research area you're dealing with, right? So, hey, is an effect size an eta squared of 0.80 big?
Depends on.
Depends. Why does it depend on the research area? You do an experiment, you get an eta squared of 0.88. Your supervisor looks at you and says it's 8-0. Your supervisor says, is that big or small? What's the fair question to ask your supervisor? Say, you tell me. You tell me, hotshot. You're the one who's been doing this for 30 years, right? I'm just a student, right? Say, I don't know if it's big or small, but this is what the numbers can, say it less confrontationally, but you know, this is how the numbers came out to be. And what are you looking for when you ask your supervisor, say, well, I don't know, is it? You're looking for what? Yeah, what's the context? And if your supervisor says, you know what? In the last 30 years I've been doing this research, everyone else has been getting 0.99. Then how big is the 0.80? Yeah, it's not big, right? But if everybody else has been getting 0.20, wow, this is big. Effect sizes have to be compared relative to other effect sizes in the area, okay? It's not like p-values. You have to say, well, I don't know, is explaining 80% also meaningful to us? If it's meaningful too, then maybe that's a reason why it's acceptably large. But compare it to other effect sizes. So, you know, the comparison is that many experiments in physics have very, very high effect sizes, not because their science is more advanced, because they control things better, right? Psychology is actually a very, very difficult science because it's even hard to measure and control things. But, you know, if they drop this and like 100 times out of 100 times it drops, they go, wow, my effect size is near 100%, right? If you do, another person across the world does this and one time it doesn't drop, you say, well, that's not bad, I still have a big effect size. No, you don't. Your effect size of like 0.98, like, it actually suggests a whole revolution in physics, but it's like, boy, that's small compared to the 0.999999 that we would expect. Does it make sense? Is it clear? Yeah. So, you know, you get the question where, you know, maybe it's not 0.99, but the person says, well, I got an effect size of 0.10. Is that big? Is that small? Maybe it's the opposite, right? Got an effect size of 0.003. Is that big? That's small? Got to compare it to other effect sizes. Why is it true that Cohen's d can be greater than 1, unlike eta squared? Can we imagine a situation? I mean, does Cohen's d have to be restricted to a maximum of 1? No. How could you justify that? Yeah, take two means. Distance is 10, standard deviation is equal to 1. What's your Cohen's d? 10. There you go. Why should it have to be bound by 1? There's no reason for it, right? So, and sometimes we look at research and we go, hey, Cohen's d, I thought effect size, you know, the more general question of effect size, I thought effect size had to be between 0 and 1. Correct your colleague. Your colleague says, I thought effect size was supposed to be between 0 and 1. What do you say to your colleague? You say, no, that's for eta squared, right? That's for eta squared, not for Cohen's d. So effect sizes are going to be on different scales and different metrics. So there's no reason why that should be like that. Is it possible to obtain a result of p is less than 0.05 and eta squared equal to 0? Think about it. Eta squared is equal to 0. Put that in your ANOVA. Eta squared is equal to 0. What's your numerator? 0. So when you're doing the test, you got your cheat sheet, okay, 2 pages, right? Put anything you want on anything at all, and you look at there, and it looks like possible to obtain an eta squared. Okay, well, what would make an eta squared of 0? You look at it. What's the only thing that makes eta squared equal to 0? No difference in means. SS between has to equal 0, right? SS total, I mean, you don't have to go into, well, SS total, what if, well, then it's undefined, so it doesn't even equal 0. So assume that SS total is equal to something greater than 0. Do the best in the question, say, well, imagine you have SS total greater than 0. SS between is equal to 0, right? What does SS between equal to 0 mean? It implies what? No separation. So write that down on your page, right? SS between implies no separation. So put on your scrap paper, mean 1 is equal to mean 2 is equal to mean 3. Okay, so the means are exactly equal in your sample. So that's true. The means are exactly equal, which means eta squared is equal to 0, okay? Got it. Now look at the next part. Can you get this? Can you get p is less than 0.05? Well, let's think about it, right? So, you see how we're working through the problem. So we go here and we say, okay, if eta squared, you've got this ANOVA table on your page, and you go, if this is equal to 0, and this is equal to whatever, this is some number, what's gonna happen when I divide this by degrees of freedom? What's my mean squares gonna come out to be? 0. Does anyone see how that has to be? It has to be 0. If sums of squares are equal to 0, whatever your degrees of freedom are, 0 divided by whatever degrees of freedom is equal to 0. Okay? So then you go here, 0 to produce your f, 0 divided by, who cares what this is? Right? If it's equal to 0, then the whole problem blows up anyways, but it's equal to, like, say 100. 0 divided by 100 is equal to 0 in that case, right? So are you rejecting your null hypothesis? Absolutely not, right? Absolutely not. You're not rejecting your null hypothesis. You're not even close to rejecting your null hypothesis because the actual separation between means is equal to 0. Therefore, can you get p is less than 0.05? No, it's impossible. Yeah.
If you have means equal to 0, would you have to run an inferential test at that point?
Okay, good question. If you have means equal to 0, if there's no separation between means, do you even have to bother with an inferential test? No. Right? There's another question, right? Kind of like on the midterm, like, you know, the means are all equal. You do the experiment, the means are all equal. Your colleague says, oh boy, I can't wait to see what the ANOVA tells us. You say, I already know what the ANOVA is going to tell us. You're not going to reject. Right? And they say, how do you know? They say, just a hunch. Right? Just a hunch because my sample means are all equal. But as soon as those sample means deviate a little bit, what becomes the master? The standard error, MS within, right? Because then you're like, boy, I've hardly seen any separation. Let's look at that standard error. Make sense? Clear. Okay. So, any other questions? So a lot of these they're very similar, right? Possible to obtain eta squared. So if you play around with those numbers a little bit, have your formulas down. Any other questions? Yes.
Could you talk through number 30?
Okay, so number 30, why are most null hypotheses is the one evaluated in ANOVA? Typically always false before we ever even begin to evaluate them. The null hypothesis is about what? Population parameters, right? Think of it. Do you think that this hypothesis is ever true? Even if you had all the data, do you think your means would be identical to one another? No. It's virtually already false even before we evaluate it. So null hypotheses, and a lot of people criticize null hypothesis testing for this reason, is we're evaluating a hypothesis we already know is false. But why is it still useful? Well, it provides kind of like a starting point, right? Like an idea. Like, it's like this, are there any coins that are fair? Probably not, because if you flip the thing an infinite amount of times, you'd probably get some difference. Yet, it serves as a nice model, right? It serves as a nice starting point. Fairness of the coin is a nice starting point to evaluating the data you did obtain. More questions? So, interaction, we see the interaction graph. Can you read an interaction graph? So there's the interaction graph. Here are the choices, what's being communicated in the graph. Presidential election polling, right? You can see where chance figures into this, right? So 52 versus 48, and then they say margin of error is 5%. Why? Because they just have sample data. Right? They just have sample data, so well, that's what they say on the news, right? They say, but it's statistically a tie. What they mean is saying we just don't have enough of a separation that we can actually conclude a real difference. Because if we sampled infinitely, maybe this would just wash out and the two people would be equal.
Could you talk about the second half of number 31, please?
Yep, sure. Regarding statistical tests, why is the probability of data given always dependent on what the null hypothesis is set at? Okay, so what's the answer to that one? The probability of the data, hey, what's the probability of getting 8 heads out of 10 flips? Depends on whether you're assuming a fair coin or not, right? How tall am I? Well, there's a measurement for it, but how tall am I? Am I a tall person or am I a short person? Compared to who, right? Compared to who? Well, it's the 8 heads out of 10 flips. The probability of that is going to be different depending on what we assume for the coin to begin with. If we assume the coin is fair, probability heads equals 0.5, then getting 5 heads out of 10 flips is what, high or low? High, right? Because we assume the coin is fair. So under that assumption that the coin is fair, 5 heads out of 10 flips, that's a high probability. 0 heads out of 10 flips, high or low? Low, right? Now, colleague says 0 heads out of 10 flips can never ever be a highly probable result. Tell your colleague what to change in null hypothesis test so that it is a probable result. Change the null, right? The null hypothesis, can zero heads out of 10 flips ever be a likely result? Yes, if your null hypothesis is that the coin is severely biased at 0 heads out of 10 flips. If the probability of heads is 0, then that's an actually really likely result, right? So if someone comes along and says, I rejected a null hypothesis, you say, what was that null you're rejecting? My data did not accord with my null. What was the null hypothesis? Right? Otherwise, somebody can just say, I rejected the null hypothesis, and if they don't tell you what that null is, then you don't even know what the meaning of it is, right? So that goes back to our binomial stuff, right? Our binomial. Yes.
This kind of goes into like reporting, like if you're reading research, are there ways that they just, a lot of times the null's assumed? Like,
A lot of
it's not
times,
always
yeah, a
stated.
lot of the times the null is assumed to be one of like a quality of no difference and things like that. But it can still be defined in different ways too, right? And that's the importance, is to kind of see how well does that null match up with the data is really what you're looking at, right? You're always looking at that. So if you tweak that null hypothesis, then the probability of the data is going to change. Okay. More questions? Okay, now for the regression stuff, the stuff we've talked about, very, very, very light testing on that stuff, right? Like maybe 1 or 2 questions on, do you understand regression? Maybe draw a plot. What would be the line of best fit, something like that, but very, very light. Very light. We still got it in terms of teaching some of it, but in terms of testing, that takes a while to sink in, so it's going to be very, very light and reasonable. So last minute study strategy is don't go study this all weekend, right? Don't go study the regression stuff all weekend. Do not study 36 and 37. Don't study 36 with any kind of real intensity. Just kind of know what we talked about today a little bit, because there'll be like maybe 1 or 2 questions, but very light. So the bulk of it is on this other stuff, and you can see there's a lot of repetition with stuff we've talked about on the midterm, right? So what have we done after the midterm? We've talked about analysis of variance. So you should know the ANOVA table, you should know some of those issues, but just work through each question, think about it. More questions on this?
Yeah. Are we turning this in on Monday?
Turn it in as anyone, you've written out answers and stuff like that? Yeah, just turn it in. We'll grade you like a 0-1. Any more questions on the exam? Questions that aren't clear here, like substantive questions? Something that doesn't make sense? Something that's like, I understand everything except for this, that would like bring everything together. Right? It's like, I get it now fully. Simple effects? Simple effects are used in unpacking that interaction, right? You got the interaction, then you look at simple effects. Okay. One of the questions on the assignment, right, that plot the interaction out. Right? Can you produce data that generate the interaction so you see what's going on in the cells, right? So you got one mean up here, one mean over here, one mean here, one mean down here. There's an interaction because the lines cross. So that gets back to looking at the interaction plot. Can you look at that plot and identify the interaction? More questions on here? Yes,
Number 19.
number 19?
Like performing factorial ANOVA versus two-way.
Yeah.
Two one-way ANOVAs.
Mhm. So when would you maybe wanna do a one-way ANOVA? When would maybe not doing a factorial ANOVA be worth it?
Identify interaction.
Yeah, one thing is the interaction effect, right? So the colleague says, I don't wanna find interaction effects. No, maybe doing two one-way ANOVAs is fine. So, for now, the identification of the interaction, hey, I don't wanna look for interactions, maybe two-way, maybe the combination of variables doesn't work either, right? So if pizza preference is one independent variable and income is the next, maybe they don't even belong in the same ANOVA. Right? So you have to think about the model building and say, this doesn't even make sense to put in the problem. So maybe doing just two analyses of variance independently is the best thing to do. Any questions? Okay, so we'll see you Monday at 8 o'clock, and you have a total of, it's a 2 hour exam, but if you absolutely need 3 hours, you can have it, but usually people are done by 2, but if you absolutely need the 3 hours, bring some food with you. Sometimes people like to think about the question, and what I recommend, do the process of elimination, right? And, they say this one can't be it. What I suggest too is you look at one question, then you go on to another question. Don't feel like you need to answer that question right away. Maybe it comes after, right? Look at the question over and over. Sometimes there's answers in the exam too. You look at question 30 and then you're like, oh, wait a minute. I know what question 2 is now. You go to question 2, you go, oh, right, it has to be this, right? Treat it like a little bit of an investigation where you're trying to slowly get to the answers. Yes.
Just verifying, it is cumulative, right? Entire semester?
It's cumulative based on this stuff here, right? So these are the things that the gateways to the questions. So everything that's on here, very light on the regression, very, very light. This weekend, don't study regression. The rest of the stuff, cumulative in that sense. Now, cumulative, p is less than 0.05, yes, that question is gonna be on it, right? P is less than 0.05 means what? Effect size means what? Interactions mean what? ANOVA table, eta squared, those things. So, what you might do is, last minute studying is prepare your sheet and put those themes down there. Put the formulas down there. So if you need to refer to them, you can. Okay, so we'll see you at 8 o'clock. These are evaluations, so I have to leave for this. We need a volunteer. And I have to hand over the class to. Who wants to volunteer as the